Okay, welcome everybody. So my name is Urban Lundin. I will talk to you about generators, and also we'll talk a little bit about linear generators because that's applicable to what we do here. But I'd like to give a sort of understanding of how a generator is constructed and what happens when we start a generator. We can view a generator as a voltage source. Here you see a voltage source in terms of a battery. So what happens? What is voltage and what is power? Is this battery producing any power? It's not ejecting any power because it's not connected to a load. So we have a voltage, which is there, it could be 1.5 volt, but the lamp here is not shining because we haven't closed the circuit. So in order for power to flow, same with the generator, so if our generator is now the battery on the left, it's not ejecting any power onto the load because the circuit is not closed. So we need to make a connection between the voltage source and the load, and then we'll have a power. So the power we can say is represented by both the voltage but also the current. If no current is flowing, there's no power. Here we have that power is equal to the product of voltage and current, and it can be expressed by Ohm's law in different ways. But current is really the representative of power. Voltage in itself is no power. If we have, for instance here, a hydroelectric turbine, it produces voltage, but it's not until connected to the grid or to load that you start to actually produce power. So how do you then produce a voltage? Because the first step you have to do is you have to produce a voltage that can drive a current. Well, the main equation here is Faraday's law of induction. So we'd like to induce a voltage in a coil, in a conducting material. So what does Faraday's law of induction says? It says that, well, the induced voltage depends on the number of turns we have times the time derivative of the flux, which can be expressed like this. You can disregard the minus sign. So B is now the flux density, which we can feel in the magnet. If we have a strong magnet, it has a high remnant field B. If it's a weak magnet, it has a weak remnant field B. So if I make a simple generator like this, it's now a linear generator. I have a magnet which is moving in some way, and I have a pickup coil. So in this coil, if I sit on the coil and I look at the magnet, I can see, okay, the flux will then change as a function of time. If the flux changes as a function of time, then I have this time derivative. If it's a time derivative, okay, it's all good. But you also see this magnet, when it comes to the turning point, it's not moving. If it's not moving, then there's nothing which changes with time, and there's no voltage. And this is something we'll come back to when it comes to linear generators. This is a drawback of linear generators. So E here is the induced voltage in coil. Phi is the magnetic flux, which is magnetic flux density times the area the coil spans. And that's really what have to change with time. We don't change the area of the coil, so we have to change B, or the total flux, as a function of time. And if we want to sort of increase the EMF, electromotive force, the E, which is a fancy way of saying the voltage from the generator, okay, we have to see what is E dependent on. It's depending on the number of turns times the flux density times the area, and then this time derivative. So if we increase the area, we get high voltage. If we increase the number of turns, we get high voltage. Or if we increase the rate of change, the derivative, we get high voltage. So if we have something which is spinning, then we can say that flux density might be sinusoidal. If I just insert the sinusoidal in this Faraday's law of induction, I get something like this. Voltage proportional to number of turns times the rate or the frequency the thing is object is spinning with, times B times A, and there's a cosines in between. So yeah, omega is the angular speed that the poles pass a point in the stator. Now, I have to say that there are several ways to direct flux around the coil in different geometries. So you can make, as soon as you see that, okay, if I put the coil here, the flux will change as a function of time, then there will be an induced voltage. So there are different positions you can actually put the coil. You can put it like here, you can put it like a tubular setup, or you could put it in a radial position, because then the flux will also change if you put it in a radial position. And that has to do with the efficiency of the generator that you want to build. So to understand a bit further about generators, here we have not a permanent magnet in the center, but we have an electromagnet. Doesn't really matter. It could be a permanent magnet that we spin. So what happens here is that, okay, the flux is now you see that there's a coil there as well, but you see that there's some other type of material in between. Now we included a stator, and the stator is really there for one purpose, or for two purposes. One is to guide the flux through the coil. Another thing is to provide some sort of stability, or where we can mount the coil. But the main reason we put stator steel there is really to guide the flux. So in this simple scenario, well, we have an induced voltage in this coil here. This is not a linear generator, but this geometry could actually be used for a linear generator as well. So what then determines the flux? Well, the flux will determine the voltage. The flux density will determine the voltage. So what determines the flux density? Well, that's actually governed by Ampere's law, which is written there, which you can express in certain ways. And this is the main reason why we want stator to sort of guide the flux. Because somewhere along this flux path, we will put a coil. And we want the flux density inside that coil to be as high as possible. So we need to concentrate the flux in somehow. And the way we concentrate it is by leading the flux density inside the stator steel. You don't have to have a stator steel. You could have an air core generator. They will produce low voltage and not so high. The efficiency will also be quite low. But from Ampere's law, you can extract, okay, what flux density will I have in my magnetic circuit, and therefore you can start it's a guide for the design of a generator. If we go back to this generator now, if we just look what for the ones I have here, what do we have? Well, N, that's the number of turns, and if I just count them there, you can count 1, 2, 3, 4, 5, 6, 7, 8. Omega is the angular speed, that is how fast we spin the magnet, or for a linear generator, how fast the periodic motion is, periodic motion. And B0 is the strength of the magnetic field, well, see earlier. A is then the area of the coil span, how much sort of flux do we get through this coil. If I want to increase now the voltage, I can multiply the number of turns. I can maybe have a stronger magnet, or I can also spin faster. If you just look what we have there, that omega n is there as well. So if I spin faster, I get high voltage. And that's a challenge for the linear generators because they have a turning point, so the amplitude, the frequency can't be too high. And just to repeat this, you can put this coil anywhere where it picks up the flux changes with time. So many topologies are possible. So just jumping ahead, this is one design of a linear generator. So you'd have almost like a rotor or a translator, we can call it now, inside. So if you take this and you would slice it lengthwise and you curve it, then you would have a rotating generator. But if you do it like this, then, well, it's a linear generator. You can say a linear generator is a rotating generator with infinite radius. That's basically the same expression. So now we have to find, okay, different ways. What's the most effective ways to put our coils in order to maximize the voltage and increase the efficiency of this one? And well, this tubular design is quite an effective way to both get the coils inside with many turns, but also get the iron inside. The iron inside has the purpose of both stabilizing the coil, but also increasing the flux density. So iron inside the generator, it improves the efficiency. The drawback is that iron is attracted to the magnets. So you also have to make some mechanical structure that sort of holds the rotor and stator, or the translator and the static part with respect to each other. The drawback is that typically induced voltage from a linear generator looks like this. So the voltage is then given by the motion, the rate of change of flux, really. And that changes because we have these natural turning points when the generator is standing still or the translator is standing still. So both your amplitude and also your frequency will change as function of time, which you see here. At the turning points, you see that the electrical frequency is very small and amplitude goes to 0. Then it accelerates, and when you have the halfway between the turning points, you have the highest speed, and also you have the highest voltage and also the highest frequency. Now the voltage is just one thing. The power is then determined by the current that we choose to draw from this device. And it's really the external circuit that controls the current, and also the external circuit controls the power. The generator is there only as a voltage source, you can say. That provides the voltage, but the power, well, how much, it's up to us to choose how much current we sort of extract from this device. So if we look on the HO project, what we have in the linear generator, we have to dimension it according to the specifications that we have. So for instance, the force now that we want to produce in this one, that will be the damping force that we have. If we take force divided by the speed, then we have the damping coefficient. So in order to match Maxwell or Newton's second equation, we need a certain damping. Well, if we multiply or take the damping, multiply with speed, then we get the force that this generator has to be able to break. And we kind of understand if we have a very small generator and we put, a ton, 1,000 kilos of pressure on that, and of course that small generator will not be able to withstand that large mechanical force. So somehow we have to have the generator be able to sort of take the same mechanical force that our oscillator is giving. And you see it depends on certain parameters here. This is another way of expressing this, the force that we have. This is a linear generator that was built then. You can see the strike length here is about 5 centimeters. In the center you can see solar magnets. You see some cables coming out from this. This is of course the cables from the coil that we can connect in different ways. And then we have some type of bearings alongside the generator here. So for this machine, this is what we got. You see that we have some voltage as function of time. You see the turning point where the amplitude goes to 0, frequency goes to 0, and it's impossible to extract any power. We can't provide any damping if the speed is 0. That's a fact. But it provides 5 volts, which is enough for these power electronic converters that we use to be able to control it. So here it says that the number of pairs depend on poles and strike length. Why do we sort of make many poles? Well, if we just have one sort of bell of the sinus here, then it provides a challenge for us to control it. So we want to have reasonably high frequency, also because the voltage is high in that respect. And the amplitude, like we said, depends on speed, magnetic field, coil, and that should be high as well. So the tests we've made, this generator was tested just mechanically. There are a lot of issues with it, but then it comes to, okay, how should we choose to draw the current from this? So we tested a passive rectifier. The drawback of a passive rectifier is that the current it draws, but then we have another proposed rectifier with about 76% higher current. So in here you see the yellow, and that's the voltage that's induced in this in the coils. For this passive rectifier in yellow here, and here in blue you see the voltage again from the same generator, roughly the same amplitude. So same amplitude, almost same frequency. The green here and the red here, that's the drawn current. So this is how much we choose to extract. So and that gives us the power. If you look on the passive rectifier now, we can see, okay, when the voltage is high, then we draw current. Voltage is high, then we draw current. But you see there's also gaps where we don't draw any currents. We have a voltage, but we don't have any current. So in places here, we don't actually extract any power, which means that the power from this device will be very, very pulsed. It will come in bursts. This is the control that we are going to use. So you can see that there's more a match between the two sinusoidal functions, and this is of course possible to extract much more power. Yes, I think my animations didn't work, so it will be. I think that's all I had to say. Thank you for your attention.